Hey engineers, it's Mr. Mathis here. I'm going to talk to you today about stress, strain, and Young's modulus. Young's modulus, we've already talked about it. It is the E in the FL to the third over 48 EI for beam deflection. So today what we're going to do is talk about how we get that number because we've just taken it as a given. And you figured it out when you did the problems where you had to take the person's weight and figure out how much the beam deflected, and then that gave you the amount for the E. But this is a little bit more specific, and it's done with what's called tensile testing. So let's start. Let's ignore that. It says, why do we need to know how a material responds to a load? Well, let's say you're making a bridge, and you watch that video on the second Penang bridge. And when you build a bridge, you have to be cognizant, you have to be aware of how the structure will move based on the forces that are applied. So when this truck goes across the bridge, what's going to happen is some of it is going to be under what's called compression. Compression means it's being pushed together. And some of it is going to be under what's called tension. And tension means it's being pulled apart. If you take your hand and you go like this, like kind of bend your hand upward, you can kind of see what happens. Like when you put a force on your hand downwards, the skin on the top starts to get all wrinkly because it's being pushed together. So there's what's called compression up here. And on the bottom, you can feel the skin start to stretch, and that's what's called tension. So when you have this this truck going across the bridge, you get compression on the top and tension on the bottom. And you can see here, for this bridge, our failure point is here. That would be a failure point in tension. The material is being pulled apart. Okay, for this bridge, the failure point is in compression. It's being pushed together. And this can happen. This right here is called buckling. And that's what happens when a material is squished together. Sometimes you'll see it, like that's how a mountain's made, first of all. But you'll see it in the road. You'll see spots where the road starts going like this, and you can see a bump, and that's where you're getting buckling. You're getting the road coming together in compression. Okay, so this is a graph, and it's one you've never seen. You saw actually on the video that you watched before this, because I told you to watch a video before this. Although I haven't made that yet, so I'm all confused. This is a graph of what happens when you take a material and try to stretch it out. Okay, you can do this to any material, but what we're going to focus on is metallic materials, because that's how we build bridges for the most part. This area right here, okay, is what is called elastic deformation. And you'll remember from the Smarter Every Day that you would have watched before this, that's like where it'll bend, but it'll go back. It'll bend, but it'll go back. It'll always go back to the way it was before. So the elastic deformation, you're not going to lose the material at that point, okay? Right here is called the proportional limit. That is the straight line portion of this graph, okay? Basically, if you pick any point on this straight line portion up to the proportional limit, that's a good point to pick for the math we'll do later. All right, right here is the yield point. This is the point at which there's no more ability to be elastically deformed at all. And then what happens here is the necking and all that stuff, where it stretches out the material over time and over the force. And this is called our plastic deformation, because it's kind of like plastic. It'll just pull apart. And then right here is where we get failure. This is where the thing snaps. Okay. So stress. Okay. You're going to want to write this down. I mean, maybe not all these words, but maybe as I'm saying it, you can figure out. I shouldn't say you can figure out. We'll talk about what's important. It says the strength of a specimen depends on the thickness of the sample as well as the material. Okay, something that's thicker is going to be stronger. That's obvious. You all know that. All right, stress is a way to calculate the strength of a material independently from the specimen side. What we're saying here is obviously a thicker sample is going to be stronger. So this is a way to figure out what any sample strength would be. Okay, it doesn't depend on the size. It's an amount that tells us how strong it's going to be based on the material. It says it is found by taking the force and dividing by how thick the specimen is, that is its cross-sectional area. And the symbol for stress is sigma, which is the Greek letter. Okay, so here on your notes, here's the equation to write down. Stress equals force, F, over A, which is equal to cross-sectional area. For most things, we're going to do this with a cylinder. Okay, and the cross-sectional area of a cylinder is pi d squared over 4. Okay, that's our stress. Okay, all right. Strain. The longer a specimen is, the longer it can stretch. Right, something that's really long, if you stretch it, if you want to try to stretch it, it's going to be easier to stretch than something that's only like this long. You've ever had, like anybody who's had braces, you get those really tiny rubber bands and they stretch a little bit. But if you get a rubber band that's like this big, it's going to stretch almost as big as your arms. Okay. Strain is a way to measure how much a material stretches independently from the specimen size. So this is another one where we're taking an amount and releasing it from the particular specimen, but basing it based on the material itself. So it is found by dividing the stretch distance, E, by the original length, L. And the symbol for strain is epsilon. So the way you would do this, epsilon equals E over L. Okay? What do those mean? E is the new length minus the original length. Okay, ln equals new length because it's been stretched out. LO equals original length. Original length. Okay. L is just the original length. So basically what you're going to do is you're going to take this is equal to, put this in parentheses on top, length new minus length original divided by the original length. Okay. All right. Young's modulus, the modulus of elasticity. This is how we've calculated beam bending and everything like that. It describes how much force it takes to stretch or bend a material. It can be found by dividing the stress and strain on a material while it is in the elastic deformation zone. So you remember, elastic deformation zone is this area, right? It's the area where the material is going to be able to bounce back, because it doesn't really matter if it's not going to bounce back. We don't want to mark that because the material is broken if it doesn't bounce back. Okay, you have a bridge that doesn't bounce back. You don't really have a bridge anymore. You have a hazard. So the symbol for the modulus of elasticity is E. So basically, E is equal to stress, which is this, divided by strain, which is the sigma over epsilon. Okay, that's how we find our Young's modulus, or modulus of elasticity. All right, what it describes is how hard it is for something to bend in the elastic region. Something that does not bend is going to have a high modulus of elasticity. Something that bends very easily is going to have a low modulus of elasticity. Something like cast iron. Okay, if you've ever had a cast iron pan or something, that thing's not going to bend. So it's going to have a high modulus of elasticity. whereas something like rubber is going to have a very low modulus of elasticity. Okay. Basically, the way we figure it out is we take the stress, whatever the stress is, and we divide it by whatever the strain is. And a lot of times the graph will tell you exactly how to do it. You just find any point in here, any one of them. Okay. Ideally, you'll find one that's on like one of the hash lines that tell you exactly the amounts. Okay. But you pick any point and you just take the number for the stress divided by the number for the strain. Any point right here, anything. All of these points are great. Any point up to the elastic deformation zone. Okay. You don't really like right here. This is a bad point anywhere in here because that's after the straight line. So you want to pick somewhere on the straight line. It doesn't matter where. Okay. All right. So here's a couple of graphs that just kind of show you or a graph that shows you what's happening. So right here, this is the material being stretched in the elastic region. This is where it's linear. Okay. Then you move over here. This part is where the material is going into plastic deformation. Okay. You can see the material has stretched. These are all the same material, right? So the material has stretched out a little bit and gotten longer because it is in its plastic deformation. Okay. Right here, this part is where it's necking, which means the material is getting thinner. And when it's getting thinner, it's going to take less force to pull it apart because the material is no longer as thick. Okay. And then here at the end is fracture. That's where it breaks. Okay. This ultimate tensile strength is the spot at which the most force is able to be put on the material. You don't want to build your bridge based on ultimate tensile strength because if you do, it's going to be in the area of plastic deformation. You're going to build it over here, okay, where it's in the elastic deformation. But this is the ultimate tensile strength where if the worst comes to worst, it's still going to survive, okay? The material is still going to survive. It's going to be irreparably damaged, but it will still be there. Okay, so here it says, give an example of material for each line. So high strength, low ductility. Ductility means the ability to stretch. Low toughness. This might be cast iron, or you could say glass or ceramic or concrete. These are all materials that are very strong, but they will not bend. Okay. Right here, this would be something like copper or steel, some sort of metal. Generally will have high strength. It'll bend a lot and it'll be pretty tough. Okay, because it'll last a long time after it's there. All right, and then last one, low strength, high ductility, low toughness. This might be like a rubber band or plastic. A lot of types of plastic will be able to stretch. They'll never go back, but they'll still be there. They'll just keep stretching. Okay. So this says, how much would an 8-foot 2x4, actual dimensions 1.5 by 3.5, in the plank position bend with a 500-pound load in the middle if it was made of the material tested on the graph? 1 megapascal equals 145 psi. Okay, so this is super tough at this point because we're not together and we don't get to talk about all of this. But I'll work it out for you. Okay, we can talk about it. So here's our material right here. Okay. And we go and we find a spot on the graph in this straight line area, right? So we got that straight line area right here and we find any spot. So I'm going to say, I'm looking really close to this. I know this is weird. I'm going to say 100. So 100 megapascals stress. So stress is like this, and this is 100 megapascals. And that's like right here. Strain, which is, it looks like just about so this would be 0.001. Okay. So 100 megapascals divided by 0.001. This is our strain. Okay. You notice strain doesn't have a percentage, or it doesn't have a unit, because we're dividing, millimeters or centimeters or whatever by centimeters. So the unit just disappears, or rather gets canceled. So to figure out the uh, Young's modulus of elasticity, we take the stress, which is 100 megapascals, divided by the strain, which is 0.001. So we're going to take 100 divided by 0.001, and that gives us 100,000 megapascals. Okay, that would be our E, our Young's modulus. Now, I would love to say that it's this easy and we just plug this in. However, since we're using feet and inches and pounds, we have to put this into pounds per square inch, PSI. So we're going to take this times 145, because it says there's 1 megapascal and 145 PSI. So we're going to take this number times 145, and it gives us 14,500,000. Okay, so our this is going to be 14,500,000 PSI. So that's our E. Okay, now it's just a delta max problem like we've done before. So delta max equals F equals L equals E equals I equals. Well, E is 14,500,000 PSI, which we just found. Okay. Delta max is what we're trying to find, because it wants to say how much would it bend. Force is 500 pounds. Length, it's 8 feet. But we need that to be in inches, so we multiply by 12 inches for every 1 foot. So that's going to give us 96 inches. And then I, it is in the plank position. So remember, plank position means that the height is the small number and the base is the big number. So that's 3.5 times 1.5 to the third over 12. So I'll put that in the calculator. 3.5 times 1.5 to the third divided by 12. It gives us 0.98. We'll just go with 0.98. That's probably good enough. Equals 0.98. Okay. Now we just plug all these in. Delta max equals 500 pounds times 96 inches to the third over 48 times 14,500,000 times 0.98. All right, let's go to our calculator. 500. Whoops. I don't like that. 500 times 96 to the third divided by, we're going to put this in parentheses, 48 times 14,500,000 times 0.98. And it gives us 0.64855. So we'll just, we got about 2 sig figs, so we'll just say 0.65 inches. So this material with 500 pounds in the middle of an 8-foot plank position would bend about how much? 0.65 inches. Okay, I hope this is helpful. I know that it's not ideal, but we'll get through it. Okay, what you're going to do for your after you take notes here is there is a a virtual tensometer assignment where you're going to go through and you're going to look at graphs just like this one right here, and you're going to figure out things like stress and strain and all these wonderful goodies.